Hello everyone, it's Aaron here, and unfortunately I apologize for the lack of videos in the past couple weeks. A lot of the videos I had pre-recorded were corrupted, but now I hope to get back on track. Wednesdays and Saturdays I will continue videos. And so with this specific video, it deals with a sequence of numbers I discovered whenever I was in junior high. And it's very interesting because I had forgotten about it for a long time, but when I refound it, I had no idea what it was, and so I started to do some research on the internet, and I found nothing, and it baffled my mind that I could find nothing. It doesn't even seem that important or big on in a mathematical scale, but it's interesting nonetheless. So let's get started. I'll show you the first six. So here they are. So you get to have a good look at the numbers. On the left side, you see x to the power of some odd number, and these will be what sequence of numbers you can get using base 10 in a certain set of digits, in a certain set of powers. Now, except for those that are divided by 3, that have a power of 3 exponentially, or 6, or some odd number that has to deal with 3, you'll get sequences of 9. For those that are like 3, you'll get sequences of 3. And these will repeat on and on and on. And it's interesting that I found out, because if you look at these, you'll see that it's all different. And I included the base power of 1, because these also have a sequence. And there's a way to get these sequences that will show you why this is also a sequence. So let's look at base 2. Or, not base 2, I'm sorry, power of 2. So, if we take 1 to the power of 2, we get 1. If we take 2 to the power of 2, we get 4. If we take 3 to the power of 3, we get 9. But if we take 4 to the power of 2, we get 16. Well, 16 doesn't exactly add up to 7 now, does it? So what I figured is I'd take all the numbers and bring them down to a single digit format. So what I did is I took 16 and then I split them apart. That's not a division sign, I'm splitting the numbers apart. So I get 1 plus 6, and then I got 7. So then I wrote down a 7. So then I did the same thing with 5. I took 5, multiplied it by 5, split them apart, and I get 2 plus 5 equals 7. And so that's where I get this number at, right here. And so I did the same thing with all the numbers, but you're going to find, like with 7, you're going to have to do this more than once. So you get 49, you split those numbers apart, you get 4 plus 9 equals 13. Well, that's not a single digit number, so we do that again. We get 1 plus 3, and then we get 4. And so that's how I got my sequence of numbers. And you can do this to the nth number that you do, and will always follow along this sequence of numbers. Now, two things will always be true with all these sequences: that the first number will always be 1, and any number divisible by 3 will always be 9, excluding this first row of numbers. So, if we use that logic where we take numbers such as 10, you add 1 plus 0 and you get 1. We take 11, 1 plus 1 is 2, and so on and whatnot. We'll get the same sequence: 1, 2, 3, 4, 5, 6, 7, 8, and 9. So with 3, it comes out to an interesting situation, because we get 3, not 9 digits. We get 189, 189, 189. So we take 1, multiply it by, to the power of 3 is 1, 2 to the power of 3 is 8, 3 to the power of 3 is 9, 4 to the power of 3 is 64. So that also equals down to 1. And so you keep doing that, you get all your numbers. So you do this up to the power of 6, and you get these 6 sequences. So you get a good look at them, and you'll realize with 4 and 2, they use the same numbers, but the only thing is that the numbers switch. However, with the sequence 5, you don't have a palindrome-like situation. And what I mean by that, whoops, it's a phone case. You cover up these last 9 digits, and so you're left with 8 digits. If you look at the numbers down the middle, you'll see that they mirror each other perfectly. 1497, 7941, 1794, 4971. They mirror each other perfectly. That's a palindrome in a numerical sense, where a number is the same forward and backwards. Where for a palindrome in a literal sense, it's a word that's the same forward or backwards. Like a taco cat or a race car. It's a palindrome. So you do this up to 6, and you get these six sequences, and these will be true all the way to the end of time. Now, I'm going to remove this, and you'll see I've done this all the way up to 12. Now when we start at 7, it starts over. The only difference is instead of 3s we get 9s, instead of 6 we get 9s, and that's because of the rule where 3s, 6, and 9s will always end up in a 9 pattern. And then you look at 8, and then it's 1, 4, 9, 7, 7, 9, 4, 1, 9, and then 9 you get 1, 8, 9, and then yada yada yada. It's the same that way too. And this would be true, I've done this all the way up to the power of 19, and so far I haven't found anything wrong, and so I believe it will go down the same way in this direction and in that direction. But then I came across something. My dad brought up a question when I showed him this, and he asked me a question: does this work in binary? And he got me thinking about all the different base numbers. And I haven't 100% proven it to me myself, but I believe in this sense that it doesn't matter about the number you use for a value in any base sense, because if you look at a squared number, let's say you take 5 squared, you get 25. Those numbers, no matter what base you use, will always be those 25 squares, or whatever base system you're using. It will always be that same number. So with that in mind, I believe that these will always stay in their base formats. There will always be a sequence that follows a certain set depending on the base system you use.